Okay, everybody's doing okay. Um, semester is it is week one still. So yeah, today I wanted to talk about galaxy morphology part two, the sub-galaxy scale. So stuff that isn't the whole galaxy wide, but actually a phenomena that happen within the disks, mostly of galaxies, but also ellipticals. And so that's the part that I want to talk about. We're sort of slowly moving away from stamp collection, where we sort of say there's this many of this kind, this many of that, and we're moving towards actually trying to understand the phenomena that we're seeing. But first off, we need to name the things that we see. So visual morphology and galaxy-wide profiles is what we did last week. This week will be subgalaxy morphological phenomena. So what all do we see that isn't all the whole galaxy, but is a clear thing in part of it. And so this is sort of my list of things that I can think of. The size is typically a kiloparsec. So a parsec is the distance to a nearby star if it moves by an arc second over the year. As you can imagine, since there are no stars a parsec away, most stars actually move less than that. But a parsec is about 3 light years, and a kiloparsec, therefore, is about 3,000 light years. So these are largish structures. So we think about bulges in disk galaxies, barred in disk galaxies, ansae, I will talk about that briefly, lenses, rings, shells, and tidal tails. And so we'll talk about what we can see and where, and what we think the origin story of those phenomena are. So we started with bulges and bars. We already had that a little bit with Edwin Hubble's classification scheme, where the prominence of the bulge basically tells you if you're an SA or an SC. So if you have a very small bulge for a disk galaxy, you're an SC. If you have a very prominent big one, you're an SA. And if really it dominates over your disk, then you're an S0. So bulge is already important, and then whether or not it had a central bar sort of tells you whether in which one of these two from the tuning fork you end up in. So this is the original sketch by Hubble, and so you can already see that you have the see the barred structure and you see the prominence of the central bulge. So bulges actually are now classified in two different kinds: classical versus pseudo bulge. So a classical bulge follows the vocular profile, what we talked about last week, the 1 over r to the fourth law light profile. So they drop off very, very quickly. Thought to originate from the very early universe. So these are sort of leftover bits of the very early parts of the galaxy. They are effectively a small elliptical. So people thought about these disk galaxies as a small elliptical with a disk grown around it. But pseudo bulges was something that was proposed much more recently. So 2012 was the big paper on that, where it's like, yeah, they look color-wise look like bulges, classical bulges, but they don't follow a divocular profile. They drop off much less prominent, and they also seem to rotate, so they don't have the random motion of stars that ellipticals are typical of. So it's not really an elliptical, it's still part of the disk, but it's just a little thickening of the disk. And there are also younger populations of stars than those classical bulges. So that we think that the classical bulges actually were a small elliptical that sort of grew a disk around it. And then the pseudo bulges is more, there was a disk and it just thickened up as you had small interactions between the different populations of stars. So it heated up kinematically. So it became thicker in the center, but not as pronounced as classical bulges. So this is how we think we can tell these things apart. And pseudo bulges seem to be incredibly common. So this is the two different, almost identical looking phenomena, but there's two different roads to Rome, so to speak. Like there's two different formation histories. So you can have a classical bulge that was made by very early in the universe by random motion, random coming together of stars, and then pseudo bulges basically grew out of the disks that host them. Bars is another thing where we think that the disk has buckled. So something has happened where there is a small gravitational interaction, or there was like a very thick, there was sort of an overdensity in the disk itself, or maybe something was a flyby, depends a little bit. But it broke symmetry, and instead of everything being on circular orbits, the stellar orbits are rearranged on highly elliptical ones. So they're going more like this rather than that around the center. And so there's a lively debate right now how long that thing lasts because, hey, do you get dynamical friction? Essentially, the rest of the disk sort of circularizes the orbits of those elliptical stars on elliptical orbits. But the James Webb Space Telescope just found one in a galaxy in the very, very early universe. I think 3.5 redshift of 3.5. So think most 10 gigayears ago, 10 billion years ago, there's already evidence of bars. So that either means that bars disappear quickly and reappear quickly, or they form and then they're much more stable. And I think we're sort of leaning towards that last scenario because about 35% of the Milky Way sized disks have a bar. Our own Milky Way has a tiny one, but we're looking straight down it. So it's really hard to say how long it is and how big it is. But there's pretty good evidence that it does have a small bar. So you have small bars, big bars, but a lot of galaxies seem to have a bar, and that 35% or sort of the large fraction of the disk galaxies have a bar, and that seems to be pretty stable. So this is a new challenge for our concept of galaxy evolution. If those things have been around for a long time, clearly whatever mechanism built them is very, very solid, right? It's good against perturbations on average. There was a really fun paper that I saw recently. It said like, yeah, there's not just a stellar bar, but there's sort of a dark matter bar underlying it. And I thought, well, dark bar is a funny word. I would call that a speakeasy, but I thought it was an interesting thing that we're now really thinking about, like how do you keep a bar like this? So on the right, you see a very prototypical barred galaxy. How do you keep them around? Some of those have a ring around them, some of them don't. So it's unclear if one of them is like a short-lived one and the other one is a long-lived one. So this is the challenge for the next um, set of observations in the next projects, really, to figure out how long those last. Sometimes, and this is back to a photograph, we get these ansae, like the spiral arms start at the end of the bar, but you have something that is a little brighter than the rest of the bar. Excuse me. Oh, pardon me. So the end of the bar has a bright little cluster at it, but they happen at both ends. And so then you have to wonder, does either end of the bar know about each other? Is that the start of the arms, or is that a start of a ring forming? So these are called ansae. I think that's a Roman Latin word, but I think it's an interesting thing that we've identified that these happen on occasion, but we have no idea why they're there, or not a particularly good idea. So they're at either end of the bar. You can see a clear bar structure, you see a clear spiral structure, and this seems to be starting the wind up to a ring, maybe. So it's hard to say. Maybe this is a part where there's pile up of gas and you just have stars forming. They seem to be fairly common. You have red and blue kinds, and so they also stand out pretty well in a color image. So maybe this is a little bit of a bias that you actually can identify them rather quickly visually. But if they're blue, for example, you can think, yeah, that's new stars, that's star formation. But others, if they're red, there must be something that is sticking around for a longer time because hasn't formed with star formation recently. Rings are another one, and we see lots of rings. Once we actually subtract the overall profile, often what's left is a little bit of a ring. So there's a little bit of an overdensity at some place. And so you can think of those as you have inner, outer, and nuclear rings. So the inner ring is sort of around the bulge. The outer ring is like much further out, is competing or is sort of the starting point of spiral arms. And then you have nuclear rings, which happen very, very close to the center. So all the way, once you've subtracted the bulge, for example, you see a bit of a nuclear ring. These often happen with resonances. So you may or may not have had resonances in classical mechanics, but if you have something I wanted to put that in here and I couldn't find it. There's a little video that I'm thinking of where you have two toilet paper rolls, you put a plank on it, and then a bunch of metronomes, and like you start them all at a random time. And as soon as they keep doing that, they start all resonating because they get forced resonancy, right? So this is a very similar thing that can happen with orbits. And it can happen with orbits in galaxies. So if you're all in a nice circular orbit, but then there is something that is asymmetrical, like for example a bar, you can end up having resonant orbits, and that moves stars from the inner parts to the outer part, and you end up with a ring. Or the origin could be tidal or something else, or a starboard shock wave. So you need a perturber most of the time. Disks are not smooth. The lumps extend, and every lump in there sort of exerts their own gravitation. So as they move around the disk, they sort of perturb the disk a little bit. And so if you have enough orbits around the center of the galaxy, then you end up with something that acts as a perturber and now has shaped the rest of the disk. So the great disturbance of the force. And so you get a resonance. And so the important part is that you get, if you have something that is a perturber, B is the perturber. And so you have, for instance, a bar going around. That's where the B comes from. So M is an integer. You take like a certain number of orbits, either it's 1 to 1 or it's 2 to 1, and then you have a frequency. And so this is the little gift that I find very useful, because are, if you are a star that is, finds a little resonance, and so here we go, and you get a certain level of pull from the bar if you are in a particular orbit. So that's becomes a preferred orbit. So stars that are close to it sort of get moved to that orbit. And you have one that is, the M is 1, and then you have the M is 2 perturbers. So a star in a bar or other perturbance as a spiral arm are in lockstep. So you can think of that same thing as in a spiral arm. Spiral arm structures moves differently than the actual rotation speed of the disks. So the spiral arms and the stars in the disk sort of overtake each other. And so you get resonances with the overdensity that is a spiral arm and the overdensity that is a bar. So you have an outer limb, and so these are called the Lindblad resonances. I'm speed running you through, which is essentially was an entire course for me, which was galactic dynamics. But a important one is that if you hear Lindblad resonances, that you go, okay, there's a perturber somewhere, and there's an inner resonance, and there's an outer resonance ring, and so that can build a ring at a particular point in your disk. So if you see ILR and OLR, that means inner Lindblad resonance and outer Lindblad resonance. So that explains quite a number of the rings that we see in galaxies. There's a bar that's happening, and that resonates so much in the disk that you end up with an outer ring and an inner ring. And so, hey, you see these things as well, because you can see these. This is a nuclear ring, and that's where there's a lot of blue happening. So you see star formation. But there's a bit of a hint of why that's there, right? You see the gas flowing in, and see that dusty gas flowing in, and that's becoming very dense clouds there. And so before it gets to the center of the galaxy and possibly goes into an AGN, an active galactic nucleus, you can have gas flow and possibly resonance from a tiny bar in the middle here. So you have this at different scales. You can have a tiny nuclear bar, and you can have a tiny nuclear ring as a result of that, or you can have this at galactic, much larger scales. Okay. And then you see something like this, right? So this is what keeps happening in extragalactic astronomy, because you go like, well, I don't see any bars, there's no perturber, and yet I'm seeing something that it looks almost like the entire disk has been moved to the outskirts, and there's just the bulge left in the center. And so you can get that. But for example, if you have a tidal interaction where you hit it right dead center, and you go, oh, that must be, the odds of that must be so high. Yeah, and here's the thing, we're in astronomy. If the odds are high, if you keep looking at a large enough number, you're going to encounter things for which the odds were very, very high, right? So very unlikely events will happen. You'll just see one or two of those. And so this is this is probably a ring of an interaction. I'll show you a little video in a second. So that's called Hoag's object. But here's the fun part, like the people from Galaxy Zoo have reported already, oh yeah, we see these. And there's other, for example, polar ring galaxies, they might be a completely different mechanism where a small galaxy fell in or a big gas cloud fell in, and you end up with a ring like that that's completely perpendicular to the rest of the galaxy. But this is what we think that happened with Hoag's object. There's a small galaxy that hit the center, and the resulting sort of tidal shock wave moved everything out to the edges of the disk. Now, this is, as you can see already from the resolution, etc., and the fact that we have two colors, this is a rather somewhat older simulation, but it does explain rather nicely if you have a small elliptical galaxy or a small dwarf galaxy that hit it just right in the center, you end up with something that moved most of the gas and most of the stars out into that ring. And I find that amazing that we A, have found a galaxy like that, and B, figured out what possibly did this. So it's, it's a one galaxy mystery. But if you do see these occasionally, so I now know of two, so probably that's the end of the list. And so we see these interacting galaxies occasionally. Hoag's object, we have an extra. So in this case, you see the yellow spirally thing. That is the one that went through. And so you can see the spiral structures that are sort of like these spoke structures that are left. But in the case of Hoag's object, we actually haven't seen any. There isn't a good candidate nearby, but we think something similar happened there. But it's a little bit of a mystery still. So those are the kind of, like, you can get ringed galaxies like that, and that might be part of an interaction. You can also have a lens or a plateau. So bars are rectangular. They're literally like, they look like a box, and lenses are much more elliptical. I find that a very subtle difference because it depends a little bit on the resolution of your image. But it doesn't have to be aligned with the overall disk. So there might be an intermediate form. So like, is it a diffusing, is it a dissolving bar, or maybe it's a forming bar? We don't quite know. So what lenses and bars have to do with each other is another thing to explore. Now I'm getting to the last bit, tidal features. And so this is sort of the miscellaneous, like with the last classification schemes, we always end up with something that is miscellaneous. And tidal features are things that have been stripped off of a galaxy that is clearly interacting with another. So if you have tides like you have on Earth, I don't know if you all had where the tides come from in physics class at some point, but tides happen on galactic scales. And so once that happens, you get that the outer parts of the galaxy are not gravitationally bound anymore to the main galaxy, so they sort of get flung off. And that's what's happening here. So you get these big tails of gas, and then also because the gas is moved and rearranged, also star formation. So you get these blue lines of stars very rapidly, bright, but very rapidly fading as the bright stars die off, the young bright stars die off quickly. So visible for a relatively short period of time while there's still stars in the tidal features, because they sort of run out of their whole gas in the outer parts. So if you have a major merger like that, let's see if this is working. Yes, okay. So this is a slightly older version, but I like it because it actually cuts back to Hubble pictures of sort of a similar configuration, because it always depends on both the camera angle. You can see that the camera angle and the time stamp, sort of the point in time that we're seeing the interaction. So here's sort of the first pass, and now we move our orientation again and go like, oh yeah, we see galaxies like that, right? So one of them is really bursting with stars while the other isn't. And so now, as the first pass has happened, we get these tidal features, and we see features like that in pairs of galaxies that are interacting. Maybe not exactly, maybe they hit each other at slightly different angles. There's a lot of variables to consider, but the fact that our simulations and the fact that these Hubble pictures look very similar, and I find it really neat that we're basically following two galaxies in their interaction, and at the same time cutting back to something that looks exactly like that in the Hubble gallery of interacting galaxies. So we get these interactions, and that sort of tells us why we're seeing all these unique looking objects. They're all essentially the same thing happening. There are two galaxies crashing into each other. Two disk galaxies are crashing into each other. And if we move that a little further than this, you actually end up that all the features, the tidal features disappear, but you end up with an elliptical. So this is a way to get from disk galaxies to one elliptical galaxy. And that was one problem because, well, uh, how do you get ellipticals that are so big and so heavy without making a lot of stars in the early universe? And it's like, well, one thing you do is you smash two spirals, two Milky Way type galaxies together. So that could be, for example, Andromeda and the Milky Way, and eventually we might end up living in a elliptical galaxy if our Earth and our solar system would actually last that long. We have another 5 billion years to do that, and I think in the next 1.5 billion years is when that interaction is supposed to get going, but it takes about 2 billion years to actually fully complete. So the night sky is going to look very different over the next 3 billion years. So but then the funny thing is that I saw a paper earlier this week that basically said, I'm not so sure that Andromeda is actually going to hit the first time. So that's also still up in the air. So you have these are sort of in the Hubble classifications were the peculiar galaxies. So a lot of these peculiar galaxies, the miscellaneous bin in his classification, are effectively interactions. These are things that didn't fit, seem very unique, like they don't seem to follow any classification scheme. And so the tadpole is something like that, and they're transitioning to something else. And so this is what we think is happening. It's interaction. It is interaction between two galaxies moving to a new to an elliptical. You get these fantastic pictures. These are very photogenic, and they're all sort of unique looking because again, it depends on when in the interaction you are, what your camera angle is, and also how exactly do they hit each other? Like, is it just a glancing blow or do they hit dead on? And so you get something like this, the rose galaxy pair, like it looks a little bit like a rose. And so, yeah, that I think you can get very romantic or very human, I would say, impressions of these pictures. But so, for example, you can see that they have very strong arms. So arms could, for example, be induced by a close encounter, not a direct hit. And tidal streams and spiral arms is something more like semantics, like which part does this stop being a spiral arm and starts being a tidal feature, right? That's a little up to you. And then, but that happens. So these happen when two disk galaxies of about the same size hit. So if you get something that is about the Milky Way in size and they hit another Milky Way, then you get these phenomenal tidal features, big swirly things. What happens if it's, one big galaxy and what's much more common, a very small galaxy? Well, it's not good news for the small galaxy. We call this a minor merger, and in the case of where it happens, also cannibalism, which I think is a bit, there's some really rude terminology in the people that study this. I don't think this is cannibalism, but it's sort of it's an accretion of a small galaxy. So we see a small blob of galaxy there and big disk Milky Way galaxy there. So what happens here is something called phase phase change in the stars in their orbit around um, the main gravitational potential of the big galaxy. And the reason for that is that the stars that fall in first start exchanging potential energy for speed first. And so they speed ahead while the galaxies that are sort of in the center of this galaxy do that a little later. So they're still catching up. So the whole thing elongates. And then the far end, so to speak, only, after everybody got a head start, then starts exchanging potential energy into kinetic energy. So you get this part where it's still coherent, but it sort of gets smeared out along the orbit that it's going to be on. And so a dwarf galaxy that was like pretty coherent and you could see as an individual blob of stars or disk of stars or what have you, essentially becomes this stream of stars around other galaxies. Now, as you can imagine, there's not a lot of star formation happening in this, right? So this is where everything just gets ripped apart, and so suddenly everything is very far apart from each other. And so the original stream of stars now gets smeared out over a very large arc over on the sky. So they're hard to detect. They're low surface brightness features. We'll talk about that more, but this is a thing that is exciting because you're hoping to see those things, but they're hard to find. So this has become a race to see how many of them we can identify. For example, this is sort of the home ec version of this, so you can actually totally see this with a small telescope. The Whirlpool Galaxy M51, the Messier Galaxy, has a smaller companion. And that's just not just happens to have a smaller companion, but there was some speculation of that, hey, maybe those beautiful grand design spiral arms, do they have something to do with the fact that there is a little elliptical, sort of floating in the back here? And so if you look at a deeper picture, you can start seeing that, yes, actually, there is already some tidal features. You can sort of see these faint wisps. If you are an incredibly dark site and you're a very patient astrophotographer, you can do this and you can actually look at this for many, many hours. And then you realize, like, yeah, there's lots of faint structure around it. There's no star formation in these, and that makes them so much dimmer. So they're very hard to see. That central bit is the Hubble picture of M51. The rest is done from the ground. So we'll revisit this when we talk about the low surface brightness. But not only that, right, you can look at that in stars, and most of the morphology that I've been talking about is like orbits of stars, the light from stars, the visible light to us. But if we go take a sneak peek real quick in gas view, and so we look at where hydrogen is sitting in this galaxy, it's not just in the disk. It's actually way more tidal features, and it has this massive spiral tidal feature, like this wisp of a tidal feature, but in gas and not so much in stars. In fact, there don't seem to be any stars associated with that tidal feature. It was just tidally stripped gas, not tidally stripped stars. So sometimes you see the evidence for this in a completely different wavelength, in a completely different telescope. And so we've done n-body simulations. This is the first time n-body simulation is, I think, the first time I've mentioned this. So you put all these particles in a box in a simulation and say, okay, these are all stars of a certain weight. Everybody sees everybody else. So you have to compute like how much gravity this star is finding from the collective of other stars. And then you calculate, where their orbits are going. So each pixel, each point has both a mass, a position, and a velocity, which is a vector. So you end up with something like 7, 8 data points per pixel. So it adds up rather fast. This is from 2000, so it's already 25 years old, but we started doing these in 1977, and that was before computers were good enough. So they actually used a room full of light bulbs and measured the light bulb distances. So Tumra and Tumra was the very first paper that talked about it. We'll talk about that a little bit more, but n-body simulations essentially looked like, you see that dashed line. That is the orbit that looked most likely for the companion galaxy to induce that spiral structure and those big arms that you saw as well, including that gas tail. So you can figure out what the orbits of both galaxies were, or the orbit of the companion galaxies were, if you try out enough different orbital structures and say, like, okay, this one's this heavy, you got a big disk here. If it goes around like that, it does a tidal induction of those spiral structure, because if you see in the insert there, that is what would happen if there wasn't an interaction. So you're like, yeah, there is a very different spiral structure happening if I have a small galaxy effectively acting like the moon on our Earth, for example. So you have like a big tidal effect, and spiral arms are a tidal feature here. So we have these visual classifications, and we go beyond stamp collecting, right? So we actually have terms for the different things. So we note the frequencies. So that's frequency studies. The first thing you can do is, if people have been out enough and got enough stamps for you to collect. So you can say, like, well, if I see 35% of galaxies have bars, that means if I make a galaxy, I have about a 1 in 3 chance that it makes a bar. So it's a pretty common phenomenon. Like, where do I see the bars? Is that in busy areas? Is that where lots of other galaxies are? Not so much. So galaxies on their own are able to make a bar as well. There might be two different mechanisms, like you can make them with a close encounter, or they can happen somewhere differently. Same thing with pseudo bulges and and classical bulges. How often do I see them? Are there lots of other galaxies nearby where I see pseudo bulges and none where I see classical bulges, for example? So can I put it in the context of what's around them? Do I need gravitational interactions? Do I need tidal forces acting on them to build them or not? And so, in principle, all the galaxy's history is encoded in the appearance. The problem is everything is in there, and there's often more ways than one to make something that looks very, very similar. So we'll keep butterfly collecting. We'll keep getting statistics on like there are this many bars, this many pseudo bulges, this many classical bulges. We see ANSEI in these environments or for these massive galaxies, and then try to figure out how that is connected to both its environment and the underlying physics. So you have to connect it back using n-body simulations and say like, hey, do we actually ever see this? Does it happen for a very short amount of time? Because that might be a reason that we don't see it very often. For example, every galaxy could undergo puberty, like some sort of puberty, right? Let's call it puberty, but it's a very short puberty. So you only see few galaxies that are doing this right now. To think of it as, let's say, bars. Let's say bars are it's just a phase. Bars are just a phase, right? That's my hypothesis. So if that's true, then it's a phase that lasts about a third of the lifetime of this galaxy. So for about a third of their lifetime, they have a bar and then it dissipates. So they happily are a disk galaxy, a bar forms, it's there for about a third of the time, and then it dissipates. It could also be that the circumstances that a bar forms is only there in a third of the cases, but then it's very, very stable and it's going to stay there. So either is the bar a long-lived phenomena that happens only in a third of the cases, or is it a short-lived phenomena that happens to everyone, but for a third of the time? That makes sense? That's the hard part to figure out. Okay, so we can start quantifying these features, like how big are they? How many of them are there? This is surprisingly difficult because we're also at the same time trying to characterize the stellar properties. So like how old are the stars in there? How much metals do they have? When did that part form? But you start realizing that some parts of the galaxy have formed much, much earlier than others. And so that bulge, for example, that classical bulge was there for most of the 10 billion years that this galaxy's been around. But the outer disk, for example, is only a gigayear old. And then all the other components sort of came along in the meantime, or are mixes of populations. So within the broad Circic profile, within the broad profile of the galaxies, the disk galaxies and the elliptical galaxies, there are many additional morphological features, especially in disk galaxies because they have this extended sort of lower surface brightness structure, and there's lots of, let's just say, lots of personality in there. And so the combination of each makes each galaxy almost unique. So you can sort of pinpoint, oh, that's that one because, yeah, you've seen it before. So it started with stamp collecting. So it started with Hubble's, tuning fork, but this many there, this many SAs, this many SBs, but we're now connecting up what kind of physics can make that, right? So the morphological phenomena are now connected to things like resonances, like interactions, like this can happen if we have a tidal feature, a tidal interaction or not. Or we can have if we see a stream like that, we go like, well, there was a small galaxy that got, spread around, but that did act on the bigger galaxy. So maybe that perturbed it enough to start having a bar or two big spiral arms or something like that. So modeling the simple images with that many components is a very complicated, very degenerate fit problem. So you can have a very large parameter space. We have all these different camera angles. We have all these possible, ways to have two disks hit each other dead on. edge on, or do they just skim each other? So there's a big parameter space, and often you can get multiple solutions for the same thing that looks pretty good. So that remains a problem, but we go right back to step one, which is make more stamps, get more of these, and see how often they happen. But also look at more distant populations, look at the bar population in the distant universe, and see what the fraction was at redshift, 7 billion years ago, 8 billion years, 10 billion years ago. And we actually noticed that, yes, there are spiral galaxies, which was honestly a bit of a surprise. We thought they were mostly going to be small and sort of Magellanic Cloud-like, or Milky Cloud-like, so like the small stuff that is floating around our Milky Way. But no, there's disk galaxies already there. There's elliptical galaxies already there. So we're sort of being surprised by the universe occasionally, going like we have a story of how these things build up, how they interact, and then, oh, this explains everything. Except that the assumption was that we started with lots of small stuff, and there is lots of small stuff, but also already disk galaxies, already older galaxies, already elliptical looking galaxies. So apparently the universe knows how to build that pretty quickly. So 10 billion years ago, redshift 4, 5, we already see disk galaxies, barred galaxies, clearly spiral structure, and ellipticals. So you get to that point very, very fast. All right, I talked a little fast, I'm afraid, but I'm hoping that's okay, because I want to keep this under 45 minutes for most talks, because you all have to go. This is sort of your lunch break. Um, does anybody have a question about what I was talking about just now? I'm going to force you to say something. I can stop the recording. How's that? That way you can just respond, and it's just me on the recording.